Yeah, hello everyone. My name is Andreas Orthey, and I'll present you our paper Section Patterns, efficiently solving narrow passage problems in multi-level motion planning. And this is joint work with Marc Toussaint, who is a professor at the TU Berlin and a fellow of the Max Planck Institute for Intelligent Systems. And this work was originally accepted as a regular paper published in the Transactions on Robotics. And in this presentation, I will talk about sampling-based motion planning. Sampling-based motion planning is a rather successful paradigm to actually automate robotic tasks. And if you look through the literature, you see it being applied to a wide variety of possible applications, like industrial automation, animation, self-driving, or manipulation. However, one of the main limitations of sampling-based methods are narrow passages. And narrow passages are basically low measure regions of the state space, which the robot has to move through to solve a particular problem. And they are super difficult to solve for sampling-based methods because those low measure regions have, of course, a very low probability of being actually sampled. And to solve such narrow passage problems is, of course, hugely important in a variety of important tasks like ingress or egress problems, where we need to either enter or escape from a trapped configuration. It is also important for pack and hold problems, where we need to fit an object through a small opening. And finally, it is also important for grasping of intricate objects, for example, when we would like to pick up something like a mug or scissors. And in previous works, we showed that you can actually tackle narrow passages by first relaxing the original problem, which effectively means that we project our high-dimensional state space onto a lower-dimensional state space. We can then solve the problem on the lower-dimensional space and use that information to solve the original problem. And one way to do that is by using geometric simplifications, where you, for example, simplify your robot geometry by using a sphere instead of a rigid body, or you remove some of the links from your kinematic chain. However, by doing this is highly efficient and can actually be used to circumvent narrow passages, this approach, still often breaks down near more complicated narrow passages. And so this means effectively, even if you have solved a simplified problem due to narrow passages, you still might not solve the original problem. And so to tackle actually this problem, we devised new tools, which we collectively call section patterns. And on a high level, section patterns basically constitute a mapping, which tries to lift a low-dimensional path into a high-dimensional space. And this is shown here in this graphic, where we depict on the top a high-dimensional space represented by the cylinder, and below a disk representing a lower-dimensional space. And once we solved the lower-dimensional problem, we get a solution path, which is shown here in green. And our contribution is basically to lift this path using section patterns into the high-dimensional space. And this lifting is robust and efficient, and the lifting happens while actually avoiding collisions and by exploiting the admissible heuristic from the lower dimensional path. And because this is very important, I will state it again here, namely that we see this lifting operation actually as exploiting admissible heuristics in a continuous domain. And to recall, an admissible heuristic is basically a lower bound on the cost to go to reach a goal region. And so this means if you solve the problem on a lower dimensional space, this provides you with an informed lower bound, which we can exploit to efficiently solve the original problem in the high dimensional state space, which basically means to lift your solution path. And if we go into the related work, we basically can exploit all the nice literature on admissible heuristics. So the question becomes of how you can exploit admissible heuristics, especially in continuous domains. And there are, of course, different tools and techniques. For example, you can use discretization techniques to directly apply optimal algorithms like A star. You can also use adaptive sampling to either increase or decrease the chance of extending a sample in your search tree. And finally, there are also continuous domain adaptations of A star. And our work is rather complementary in that we concentrate on path heuristics, which are basically an important subclass of heuristics. And concerning those path heuristics, there are actually several important papers on this topic. Those path heuristics are also often called guide path approaches, which are often used for high-dimensional humanoid robots. And it is, of course, hugely important to be able to detect and escape misleading heuristics, or even to do infeasibility tests to verify if a heuristic is not working at all. And those approaches are also closely related to methods which try to model narrow passages using workspace information. And our work differs at this point by us concentrating on bypassing actually narrow passages, which we do in a reactive manner. And we do that also by not modeling narrow passages at all, because we found it to be rather inefficient in higher dimensional spaces. So let me get into the approach itself. So with section patterns, we basically assume that a path on a lower dimensional space is given, and you want to lift this path into a high dimensional space while respecting collision constraints. So the question is, of course, how do we actually do it? And we have studied this topic extensively, and we came finally to the conclusion that there are at least 4 distinctive patterns which are super useful to actually do this lifting. And we call those patterns Manhattan, wriggle, tunnel, and backstep pattern. And I will explain each of them quickly, and then I will talk about how to combine them to actually efficiently do the lifting. And this leads us to an algorithm which we call pattern dance, which actually coordinates the execution of those patterns. So let me start with Manhattan pattern. With the Manhattan pattern, we interpolate a high-dimensional path, but we do that by actuating the least amount of joints during interpolation. And the reasoning here is, of course, that less joint actuation means less movement of the robot body, and less movement of the robot body in turn means less swept volume of the robot during execution, and a lower swept volume means directly that we have less chances for finding collisions. And this chain of reasoning was basically first expressed by a nice paper from Cortez in 2008. And the second pattern is the wriggle pattern, where we basically do coordinated random walk steps to improve locally our path. The motivation for this pattern comes, of course, from the way of how we often try to open, for example, a door by just trying to wriggle the key forward. And the wriggle pattern is basically our attempt to formalize this motion primitive in a more mathematical way. And very similar to this wriggle pattern is the tunnel pattern, where we do not do a wriggle motion, but we execute a small sidestep motion, which basically means that we move the keys sideways. And when we visualize this in joint space, we often see that this actually helps us to circumvent small infeasible regions. And finally, we have the backstep pattern, which we only execute when we are fairly certain that we are trapped in a dead end. An example would be a dog with a stick, which cannot move through a tight opening because the stick is blocking the way forward, as you can see here on the left. And here the dog would have to make this cognitive leap of stepping back, turning, and then trying it again, like on the second video here. And we model this motion again mathematically, which allows us to make a coordinated back step to move actually forward. And this is just something which works pretty well due to the nature of narrow passages, which often have actually small cavities in state space, which we have to escape from. And this is visible, for example, on the right, which shows a slice through the configuration space of a small rectangular robot near to a narrow passage, which is shown here on the bottom of the page. And this figure here on the right shows several cavities in which we could actually get stuck when we move forward, and this backstep pattern helps us to actually avoid that. And finally, we of course need an algorithm which can coordinate all those patterns in a meaningful way. And for that, we developed the pattern dance algorithm, which basically starts applying the least computationally demanding pattern. And if that doesn't work, it would successfully try out more and more demanding patterns until we find a feasible lifting or until we reach a termination criterion. So in super simplified pseudocode, this would actually basically be a loop in which we check if one of the patterns successfully solves the problem. And so we basically just iterate over all of them, and we terminate once the termination criterion is reached. So finally, let me come to the evaluation. We evaluated our method on several challenging narrow passage problems, like the bug trap on the top left, a double L shape, which has to fit through a small opening, a kinematic chain where we have to escape from a trap configuration, and of course, a generation of grass poses using the shadow hand robot, which has 37 degrees of freedom, and which we evaluate on 4 challenging grass poses, which have to be reached from an upright position of the robot. And to make a really comprehensive evaluation, we try to benchmark this method against all planner in the open motion planning library. And at the time of doing the benchmark, there were 36 planner implemented apart from ours. We then use the section pattern inside of our algorithms to compare against all the other 36 algorithms. And we found out that our approach can outperform all other approaches by up to 1 or even 2 orders of magnitude. And in this table, you can see that most other approaches usually time out at our time limit of 60 seconds, which shows that those problems are really, really difficult and that most planners cannot even find a single feasible solution. And to illustrate how we solve those problems, I'd like to show you 2 videos. The first video shows the solution to a bug trap problem, where we need to escape from a trap using a cylindrical robot. We first find a solution to a small sphere inscribed in the robot. And once the solution is found, we then lift this path using our method to the higher dimensional state space, and this produces the solution to the whole problem. And you can see here that during the execution, we also executed the backstep pattern to actually enter the narrow passage. The second video shows the steps to find solutions to the grass poses. We again quickly search for a simplified solution path, which is shown here. And once those paths are produced, we again use our methods to lift those paths up into the high dimensional state space of the complete robot. And you can see here basically the execution of the whole trajectory paths. And in conclusion, we presented section patterns as a toolbox to lift paths from a lower dimensional space to a higher dimensional space. And we did this by exploiting the admissible heuristic given by a low dimensional path through patterns like the Manhattan, wriggle, tunnel, or backstep pattern. And in our evaluations, we found that the runtime of this approach actually improves planning by 1 to 2 orders of magnitude, which significantly speeds up planning when narrow passages are present. And while this works pretty well for the problems we considered, we believe this approach could also be useful to further probe and understand high-dimensional state spaces, which would allow us to scale sampling-based motion planning techniques to even more complicated and complex applications. And with that, I would like to thank you for your attention, and please do not hesitate to contact us if you have any questions about this work. Thank you.